Good afternoon and evening for some of you. It's my pleasure as the president of AGU's Earth and Planetary Surface Processes section to introduce this year's award winner of the Luna B. Leopold Early Career Award. It is given annually to an early career scientist in recognition of a significant and outstanding contribution that advances the field of Earth and planetary surface processes. It's named in honor of the incredibly famous Luna B. Leopold, who engaged and nurtured young scientists throughout his distinguished career in hydrology and fluvial morphology. This year's award winner is Jaap Nienhuis for contributions to the study of coastal geomorphology, particularly the processes and feedbacks that form and evolve deltas, tidal inlets, and bed forms. He received his PhD from MIT Woods Hole in 2016, a master's from the University of Twente, a bachelor's there also, and did a postdoc at Tulane. From the nomination package, his research combines field observations, remote sensing, and model simulations. He's been an associate editor for JGR Earth Surface and conscientiously oversees the review process of manuscripts focused on deltas and coasts, demonstrating a strong commitment to stimulating progress in the earth sciences. He's received the prestigious Denny Award, which allows him to expand his theoretical framework to predict global river delta change in the coming century. He continues to pull people together for collaborations of various kinds, serving as an energetic source of inspiration within his rapidly growing network. One paper in particular stands out. In 2015, published in Geology with his co-authors Ashton and Glisson, What Makes a Delta Wave Dominated? It's an unprecedented achievement in our field, according to the nominators, in that it introduces a simple delta model that has genuine predictive capacity beyond what generally may be expected from the more complex state-of-the-art morphodynamic models. Earlier this year, Jaap's scientific endeavors culminated in a Nature publication that offers a process-based quantification of Galloway's qualitative ternary diagram depicting the relative influences of waves, tides, and rivers on delta morphology. Join me in congratulating Jaap for his amazing achievements and for his future growth as a scientist and contributor to our community.
All right. Well, my name is Jaap Nienhuis, and I'm very honored and excited to present to you this year's Sharp Lecture. Before I begin, I'd like to say that this really has been a collaborative effort. I had the pleasure and honor to work with a great group of students and postdocs for the past couple of years. So you'll see some references of their work throughout the talk. But there's definitely, of course, more to come in the future, so keep your eyes out as well. I'll be talking about testing morphodynamic theories by comparing and contrasting river deltas. And what do I mean by that? Well, you see a couple of pictures here of river deltas, and you see there's an amazing variety of shapes and forms out there. And I think we can learn a lot by looking at differences between these shapes and putting those differences in their respective environments. And by doing that, I'm going to show you that we can test morphodynamic theories of how deltas form and adjust their shapes as well. And we're really not limited to these famous deltas I'm showing you here. We can go all across the globe and see that river deltas dot Earth's coastline, that there are thousands and thousands of river deltas. So for example, I can zoom in to the North Shore of Alaska, where Overeem and Anastasia Poliouras, for example, did some amazing work studying river deltas. And you see on the right-hand side, you see the Mackenzie River Delta, fairly big system. But we can zoom in and see a slightly smaller Colville Delta, and zoom in further and find deltas appearing in many scales across Earth's coastline. So there are tens of thousands of deltas, and we can really use the magnitude and the scale of all of these systems to test our theories and put forth new hypotheses of how deltas change. And ultimately, what we're hoping to do is to look at deltas through the lens of boundary conditions of their environment forming deltas. So for example, you see a system here where there's a river draining into a coastal zone with some sort of river discharge and sediment load and grain size. Of course, there are waves and tides and sea level fluctuations acting on the basin side of the system. And if we can do that predicting very well, if our theories are very good, we might be able to then predict what kind of morphology would result from the combination of these different factors. So if we do that really well, in this case, we could potentially predict some morphological attributes of the Mississippi River Delta. And by studying a river delta through these boundary conditions, what we're also able to do then is to say, well, what if tides change in the Gulf of Mexico in the future? What kind of morphology do we expect? And if there's then a changing morphology, we can then make inferences of how we expect the Mississippi River Delta to change into the future. It's of course important to note that studying river deltas through these boundary conditions has had a long history, including, for example, Galloway in the 70s and Wright and Coleman as well. And they formed this classic delta triangle or a ternary diagram where they casted river delta morphology as a combination of rivers, waves, and tides acting and creating delta morphology. And so my work really builds on those early concepts. So the three morphologic theories or hypotheses I'd like to discuss with you are first, alongshore sediment transport and how that controls delta protrusion. Second, tides and river discharge, how that creates delta channel width and perhaps is a signature of the influence of tides on deltas. And third, I'll go into a recent work on sediment fluxes and sea level change, and if we can use those to perhaps predict or think about delta growth and delta land loss. And lastly, I'll try to integrate these theories to say something comprehensively about delta morphology. So first, alongshore sediment transport. This is a study I'll be talking about that I published together with Andrew Ashton and Li Vijay Sun from the Woods Hole Oceanographic Institution. And they were my PhD mentors. So this is from when I was still a PhD student. And we looked at this environment I'm showing you here, where there's a coastal zone with river sediment supply feeding it and waves acting on delta deposits. And I again drew this black box because we're trying to predict delta morphology from these boundary conditions. So without looking at delta morphology a priori. And this is in an environment without many tides. And in environments like this, there have been studies that show that cuspate deltas form because there is an influx of sediment into the coastal zone, and then alongshore sediment transport from waves, moving sediment to the left and right, and forming these cuspate deltas. And as you can see, the delta with steady sediment supply increases through time, but the shape, the cuspate shape maintains, the shape is maintained over time. What we also know is that alongshore sediment transport can be described with formulas like the one I'm showing you here, where the alongshore sediment transport is dependent on a sediment transport coefficient K, wave height to some power, wave period to some power, and then a portion that is dependent on the relative wave angle between the coastline and the incoming waves. And that is represented by this figure here as well. So you see that waves move the maximum amount of sediment at about 45 degrees when they hit the coastline at about 45 degrees. So can we combine these two concepts and perhaps make an assessment of the resulting delta morphology from waves and from fluvial sediment supply? Well, we can make the simple kind of first order assumption and say, well, of the fluvial sediment supply, about half will go to the right and half will go to the left. And if we then rewrite this equation, we can see that the morphologic unknown in this case, that the orientation with which waves approach this coastline that we haven't observed yet, is driven by fluvial sediment supply on one hand, and then a factor representative of wave processes on the other hand. So Q river is going to increase the angle, and then HS and the wave period are going to decrease this angle. And then, of course, importantly, we can remove this black box and then test our theory by actually measuring the angle at which waves approach the coastline. So what does this testable prediction look like? Well, for ratios of Q river over what we call Q wave, so HS and TP, between 0 and 1, we see that the delta shoreline angle gradually increases over time and gets pointier and pointier up to an angle of about 45 or 50 degrees in this case. However, it's important to know that this ratio is not limited to being between 0 and 1. You can, of course, have bigger deltas with higher fluvial sediment flux. And in that case, our theory doesn't predict any angle because there is no angle with which waves can move that much sediment away. The cuspate shape is no longer stable. So in that sense, we predict river-dominated deltas to form. And then as part of this study, we looked at a bunch of deltas along the coast of Java. And we indeed found that this ratio is a fairly good descriptor of wave-dominated deltas becoming pointier and pointier closer to this ratio of 1. And then when you exceed 1, then river-dominated deltas form. We also looked at other deltas around the world and see, for example, in the lower right corner here, the eel, whereas there's no shoreline protrusion at all. So we predict that the wave-driven sediment flux, or the potential wave-driven sediment flux, is much greater than the fluvial sediment supply through the eel. And on the other hand, we have the Mississippi, where you see, of course, there's no cuspate shape anymore, because we predict that under no angle can waves move enough sediment away to form such a shape. So we predict a river-dominated delta. We later expanded this theory to look at other combinations of wave energy, so not simply kind of 50% of the sediment flux going to the right and 50% going to the left, but cases where wave approach from one angle predominantly, so there's asymmetry in the wave climate. Interestingly, we found it doesn't change the transition to river dominance very much, it just adds a net flux on top of the river flux. But it has other interesting effects. It can, for example, steer the river channel away from or into the waves. Another thing that I think is very important from this study is that we can learn a lot from the noise. So we found that it's in general a very good predictor, but scientifically, I think a lot of the interesting learnings come from wherever our theory didn't fit what we finally observed. And that's the case, for example, for the Tinajones along the Colombian coastline, where we predict an R of 2. So we predict a river-dominated delta to form, but instead we see the smooth shoreline shape indicative of alongshore sediment transport in a wave-dominated delta. We can look at what happened in this case because they have beautiful aerial imagery going back to the 30s, where this river meander broke through the coastline and started building this river delta. And you see that indeed initially a river-dominated delta formed, but over time river dominance was reduced and shorelines became flatter and more indicative of wave processes. And we think this is the case because as you split your river channel, you split the amount of fluvial sediment going through each river mouth, but your potential for waves to move sediment away from each river mouth stays the same. So in that sense, you can bifurcate yourself into wave dominance, even if the R from the delta apex is still greater than 1. So there are certain cases in which delta as a whole might be river dominated, but through splitting, it is bifurcating itself into wave dominance. But of course, this doesn't explain everything because there's still a lot of other dynamics going on here that we're really not sure about. For example, if we look at a recent picture from 2019, we see that one of the channels silted in. So wave processes at the downstream side prevented this channel from remaining open. And in this sense, that there's still a lot of work we can do studying this delta. Another hypothesis or theory I'd like to discuss with you is how tides and river discharge set delta channel width. And so I'm showing you two pictures here, one of the Mississippi River, which is typically cast as a kind of end member river dominated system, and the Fly River on the other hand, which is typically thought of as a tide-dominated delta. And one of the kind of geomorphic signatures that shows this very nicely is if you look at channel width from upstream going downstream. And you see that the Mississippi channel width stays fairly constant over time, over space going downstream. But the Fly River on the other end starts out being much narrower than the Mississippi and ends up being much broader. And that is, of course, due to tides. You have not much tidal amplitude at the Mississippi river mouth, and so there's not much tidal discharge either compared to the river discharge. On the other hand, for the Fly River, you have a very high tidal amplitude, creating a lot of tidal discharge, which necessitates a very wide river mouth to convey all that water going back and forth. However, this is, of course, not yet a testable prediction for delta morphology. So in a study I did together with Tor Tornquist and Ton Hoytink, my two postdoc mentors, we looked at how we can create a morphologic prediction for this mouth width based on these boundary conditions. And we did that in this case by formulating two formulas for the tidal prism. The first is very simply the tidal range, so twice the tidal amplitude times the average width of the estuary and the length of the estuary. So that combined makes it a volume of water that has to drain through the river mouth each tidal cycle. What we also know is that we can write the tidal prism based on hydraulic geometry. So hydraulic geometry says that the tidal prism that has to go through the mouth every tidal cycle the hydraulic geometry says that the tidal prism that has to drain through the mouth every tidal cycle is intimately tied to the cross-sectional area of the mouth itself, with the inclusion of a sediment transport coefficient, K in this case. So this gives us two formulations for the tidal prism that we can then write and rewrite into a predictive equation for the width of the mouth. And you see in this case, this green formula here, that the mouth width is predicted to be some upstream width plus an addition due to tide. So that beta KAL is a component of the width because of tides on the downstream boundary. So for the Mississippi in this case, of course, that latter part, the beta KAL, is very small, and the width of the mouth is about the same as the width upstream. And for the Fly, this is the dominant factor. And having this a priori prediction, we can then also cast it into a prediction for the tidal discharge through the mouth as well. And if we multiply that by CS, by sediment concentration, we get a tidal sediment flux, for example, in kilograms per second, draining through the mouth at each tidal cycle. And this is, again, an a priori prediction without having to observe the delta itself. So what is the testable prediction in this case is we can formulate a ratio T, for example, where this is the tidal discharge divided by the river discharge. And if that ratio is very small, we predict that the river width divergence is going to be 1. So the mouth width is not much greater than the upstream width. On the other hand, on the other extreme for tide-dominated deltas, Q tide is much greater than Q river, and we predict the mouth to be much wider. And the exact relation here depends a little bit on other factors such as the tidal angular velocity, things that we can also capture beforehand based on tidal boundary conditions. But we see in this case, when we measure this for a bunch of different deltas, is that it's a fairly accurate predictor, and we can capture a lot of the variation in tidal delta morphology throughout this range, going from the Ebro and the Mississippi that are classically river or wave dominated, all the way to the Thames, the Fly, and the Ord that are very tide dominated. So again, this is a predictor of morphology, of the morphology of deltas based on boundary conditions. But as you see here, there's still a lot of scatter, and I think we can still learn from a lot of the scatter or noise around these relationships. And one of the kind of avenues we're going into now in a study with Jasper Leuven and Daan van Keulen, Alberto Canestrelli, and Tom Hoiting, is looking at depth profiles through this river to tidal transition. And we see that for various combinations of river and tide, this highly nonlinear interactions between tides and river can create very complex profiles that are not embedded in our simple formula that I showed you earlier. And you can create deep scours as well that are very non-intuitive. We're hoping at some point to combine this with a recent cool study that came out by Kieran and Jerolmak that showed that you can capture width of rivers by looking at the strength of the bed versus the strength of the banks. The last hypothesis that I like to go through with you is sediment flux and sea level changes and how that controls delta growth. The video that you see here is from a cool paper by William Anderson and others that came out last year. And it builds on a lot of earlier work as well from Muto and Steele and Parker and others. And it shows you a cross-section of a delta subjected to fluvial sediment flux from the upstream and sea level oscillations on the downstream boundary. And what a lot of these studies show that have been validated through experiments and through modeling is that if you want to look at delta growth over time through sediment flux and sea level changes, the relative importance of sediment flux and sea level rise is going to govern delta growth. So if you have relatively a lot sediment supply compared to the sea level rise rate, you might still be able to grow your delta and gain land. However, if sediment supply is reduced, your delta growth might be reduced. And if your sediment supply is small compared to the sea level rise rate, you might have delta land loss as well. So this gives us a prediction about the amount of land area growth or loss for deltas. However, and this is kind of an interesting paradox for deltas, but I think for coastal geomorphology in general, where we know that sea level rise is a very important control on coastal change, but through the instrumental record through the past 30 or 40 years, it's been very hard to kind of figure out the signature of sea level on coastal changes, to distill the exact amount of change that sea level has been controlling. And that is in part because sea level rise has been relatively small compared to other changes along coastlines, such as human interference or wave action or tide action. And another kind of issue with trying to see the effects of sea level rise on deltaic shorelines has been that for one particular delta, of course, sea level rise is not going to fluctuate spatially very much. So it's very hard to distill a relatively small constant signal throughout delta shoreline dynamics. So to overcome this and to test this hypothesis that sediment flux and sea level changes control delta growth, we instead tried to kind of a bigger data approach and compared the behavior of different deltas to one another. What you're seeing in this map here is part of a recent paper that is currently under review together with Roderick van der Wal. It's currently on Earth Archive. And we took data for about 11,000 river deltas globally. And we took cross sections for all of these river mouths to try to test this prediction that sea level and sediment flux controls delta growth. And the big advantage of that is that if we have so many deltas, some deltas are going to be in areas such as the Hudson Bay or in Scandinavia where sea level rise or sea level is going down, so that there's sea level fall. And in other places like Southeast Asia or other deltaic coastlines, in other places, there's been very high subsidence. So the relative sea level rise rate in those cases is very high. This gives us a very broad range of relative sea level rise that can very well kind of improve any signature of sea level we're trying to find in delta change. Of course, for predictions, we also need fluvial sediment flux. So we have data from WMSED. This is a sediment flux model, a globally gridded sediment flux model developed by Sagi Cohen Albert Kedner-Jai, Savitsky, and Balash Fetica, and others, and published in 2013. So we have fluvial sediment fluxes for all river deltas as well. And so what then is the testable predictions based on this data? Well, we took an even simpler approach from the earlier studies by Muto and Steele and Parker. And we said that delta growth is a function of the amount of fluvial sediment feeding a delta minus the amount that is likely going to be trapped on the delta plane. So that's the delta area times the sea level rise. It's kind of the accommodation space created from sea level rise, and that is going to limit the amount of sediment flux that arrives at the coastline. So whatever sediment flux you have left, if you divide that by the depth of the foreset, that's going to give you an expected delta growth rate in square kilometers per year. On the other hand, if the fluvial sediment supply is lower than the accommodation creation on the delta topset, then you're going to be left with a sediment deficit. And if you divide that by the amount of sea level rise on the delta topset, that could give you an indication of the amount of land loss in square kilometers per year. So if this theory fits very well, then it's on this one-to-one line. We actually took some observations based on the remote sensing data set for all of these 11,000 deltas as well to test this prediction. So what you see here are snapshots of the Mississippi River Delta and of the Yangtze Delta as well, where blue pixels represent land that turn into water, so land loss, and green pixels represent water that turn into land, so land gain. So you see the erosion along the Mississippi and the infilling of a distributary channel of the Yangtze here as well. So we have observations of net delta land gain and land loss for these 11,000 systems, and we can use that to test this theory. What we find is that we do a fairly good job and explain about 30 or 40% of the variance between deltas and delta growth rates. So this is a very good test, and it potentially allows us to give very broad scale forecasts or hindcasts of what deltas might do under different sediment or sea level scenarios. And so we're very excited about this. But as you can see, and this is something I'll reiterate later as well, is that we can learn a lot from the scatter here in this case as well. So what can we learn from the noise? Well, one of the avenues of work that I'm currently getting into is one of the simplifying assumptions we made earlier to predict delta growth rate or delta land loss. And that is that all of the sediment fed to the delta was retained within the delta profile. And we know from countless field studies and other observations, for example, by Chris Esposito, published in 2017, that this is definitely not necessarily the case. And a lot of the sediment might be lost from the delta prism further out into the sea. What we've done here is kind of made the inverse relationship and say, well, if we know the amount of delta land gain or delta land loss, we can convert that to an estimated amount of sediment trapped within the delta. So that's what I'm showing you here. On the y-axis is the inferred topset deposition. So that's based on Landsat observations, how much we expect that was trapped within the delta profile. So within the delta topset in this case. And on the x-axis is the fluvial sediment supply fed to the delta for that same time period. And of course, if 100% of the sediment is trapped, you'll find everything to be on that one-to-one line. And instead, we find that most of these 11,000 deltas actually plot way below that one-to-one line. So that means in that case that some of the sediment is lost from the delta profile and doesn't make it to add to delta land gain in this case. And we can learn a lot from this noise. For example, we can see how this delta sediment retention varies between different environments. So if we plot this retention fraction, for example, for different wave heights, we see that for low wave energy environments, a lot more sediment is retained within the delta profile compared to very high wave environments. And so in very high wave environments, a lot of the wave action might lead to a reduction in the delta land gain efficiency. Interestingly, we find something different if we look at different areas of tidal amplitude. And we see, for example, that for very low tidal amplitude, there's not very efficient delta land gain. But in cases of very high tidal amplitude, there might be a lot of wetland creation, for example, leading to relatively high land gain efficiencies for the amount of fluvial sediment feeding a river delta. So lastly, I want to discuss all of these three theories I just talked about and see if we can say something comprehensively about river deltas and river delta change. Well, throughout the talk, I discussed these different sediment fluxes, Q wave and Q tide, and the effect on sea level rise on the fluvial sediment flux. And you can cast that in that diagram I'm showing you here, where the relevant sediment fluxes is the fluvial sediment flux feeding a delta minus whatever is trapped because of sea level rise, and whatever is left at the river mouth is going to be redistributed by tides going back and forth, widening the delta and widening the river mouth. And it's going to be redistributed by waves moving it along coast away from the river delta. So this is really a sediment flux balance around the river mouth of a particular river delta. We can cast this back in this Galloway triangle that I talked about before, where the three relevant sediment fluxes in this case, Q river, Q wave, and Q tide, represent the river, wave, and tide forces of Galloway's original diagram. And they give us two morphologic predictions depending on where you are in this triangle. For example, where you are along the left leg of this triangle tells you something about the delta protrusion angle, so the pointiness, and where you are along the Q river to Q tide leg of this triangle gives you a quantitative prediction of the amount of delta channel widening. And because these are all predictions based on boundary conditions, we can do this fairly easily for the 11,000 deltas I discussed before. We got wave and tidal information, and then for these 11,000 systems, we placed them quantitatively within this delta triangle based on sediment fluxes. And the size of the marker here denotes the amount of fluvial sediment flux, so the proxy for the size of the delta. And you see that most of the smaller dots are in the wave-dominated corner. So most of the smaller deltas are going to be wave-dominated. But if you look at the bigger systems, they're heavily skewed to being river or tide-dominated. Now, river-dominated, of course, makes sense because that's what's controlled river dominance to begin with, this Q river. And tide-dominated because a lot of the bigger systems are fairly low-sloping, which is conducive to a very high tidal prism and therefore also a high tidal discharge. What we can also do, aside from making morphologic predictions about delta channel widening and delta protrusion, is to see if there are any empirical predictions that also fit within this triangle. So for example, what I'm showing you here is the same Galloway triangle, but then for a couple of deltas, we just simply counted the number of distributary channels, and we plotted and see if we could find trends within this ternary diagram. And interestingly, you see that when you fall below a line dictating Q wave versus Q river, so if waves become dominant versus the river sediment flux, you quickly reduce the number of stable channels on your delta to about 1. If you fall below that line, if you fall above that line, you get into river-dominated or tide-dominated deltas that can bifurcate and maintain multiple channels. With the caveat, of course, because a recent cool study just came out by Gerald Salter and all, denoting some of the limits on predictability of delta morphodynamics. So that's really something to take into account as well. The other cool thing you can do with this, aside from making static predictions about delta morphology as it is today, you can also use these fluxes to think about delta change based on changes in boundary conditions, something I alluded to at the start of this talk also. For example, we might think that sediment fluxes might change into the future. Wave climates could change as well, of course, because of climate change. And in the Arctic, a lot of other things can happen because of sea ice, other permafrost, for example, on delta plains. That might change the location of a delta within this triangle. For example, you can have deforestation increasing the fluvial sediment supply to a delta, and where you would therefore predict an increase in river dominance for your delta. You can have an increased storminess, increasing alongshore sediment transport and reducing the protrusion of your delta. And similarly, you can have sea level rise that leads to more trapping of sediment on the delta plain and a reduction of sediment supply to the river mouth, and therefore an increase in wave or tidal processes leading to a reshaping of the delta plain. You can combine all of these and look at what the delta trajectory might be for changes in boundary conditions, with the important note, of course, that a delta might respond very, very slowly to these changes in boundary conditions. Right? Boundary conditions change on a daily or seasonal time scale, but delta morphology does not. For example, you can create a diffusion time scale based on alongshore sediment transport fluxes, where you can say, well, the time scale for a delta to change is likely related to the size of the delta squared, divided by the diffusivity of waves. If you do this for a fairly small delta in an energetic wave climate, you get into a regime of about 100 years. So it might be multiple decades to centuries before a delta can adjust its morphology. So all of these changes happening to deltas currently, deforestation, increased storminess, and sea level rise, might all be reflected in delta change at the same time. And the last thing I wanted to show you is that I'm a big proponent of open science, and all of these predictions that I've been showing you are freely available, and the code to reproduce these findings is available as well. You can find it on GitHub, and there's also an Earth Engine app that is also mobile friendly that you can look at these different river basins and predictions for river deltas, including land area changes observed for the past decades. So thank you very much. Thank you for attending. I'd like to thank funding agencies, National Science Foundation, NWO, the Dutch Organizations for Science Research, and the American Chemical Society for making a lot of this work possible. I would also like to give a huge thanks to a lot of the collaborators and science friends and others that have contributed to this or other areas of research. And across many, many time zones, you really make delta research a fun endeavor. And lastly, I'm not sure how the Q&A is going to work, but definitely shoot me an email or talk to me on Twitter if you have any questions or thoughts, or just like to talk about river deltas. Thank you.
Thank you. It was an excellent talk. It was compelling, exciting. Congratulations to you. Well done. Marvelous for the award, the Leopold Award job, and for a talk that I think people will be discussing for many days. I'm already getting text messages from people saying, what a great talk. I'm going to do one.
Thank you.
You're welcome. I'm going to do one thing that's just a logistical issue, and then we'll turn this to the questions. For everybody out there, there is a reception this evening. A number of people in the EPS community have worked hard this week to put together an event for us. It's being, the platform that we're using is Wonder. So if you look in the chat box, you'll see a link, and there's a password. So you can get to our reception party after this event, and you can speak with Jap there even. Right now, we'll focus on the questions that we've been getting. We have quite a few coming in. I'm going to start with one from Bill Dietrich. On the Fly River, how do you know what the tidal discharge should be? Isn't that a function of the channel widths? And did your hydraulic geometry assumption partly insert an answer? I'm happy to repeat any of that again if anyone.
Yes, no, I'll try to. That's a good question. Yes, so of course the tidal discharge and channel width are intimately connected through hydraulic geometry. So that's definitely an assumption that we're making. Although that there are theoretical predictions or theoretical ways to predict hydraulic geometry based on, for example, the shield stress. So in the sense we assume hydraulic geometry, but you can also test hydraulic geometry in other systems and settings. I hope that answered his question.
Yes, and so far we have about 5 or 6 questions lined up. And Bill, if you want to follow up on that later, please put another note in there. And we could always continue with that question if you'd like. I'll move on now to one from Jonathan Warwick. He first says, fantastic body of work and lecture, congratulations. How have humans influenced the data, and are they part of the noise?
Yeah, well, it depends on, I guess, how you look at it and what your field of study is. But yes, so the humans are definitely part of the noise in some of the scatter plots I've been showing you. And so the question, I think I can. So yes, humans have influenced the, of course, delta morphology, and the way I've looked at it so far is the effect of humans on boundary conditions. So, for example, deforestation and river damming are two good examples, of course, increasing sediment supply and therefore affecting delta change. But humans, of course, do a lot on the delta plane itself as well. And that's work that's equally important, but I've had trouble making quantitative predictions of that for delta morphology. We're looking into it, but I definitely don't have an answer yet in how to do that theoretically.
You mentioned dammings, and there's quite a bit of work on reservoirs, and especially the large modern reservoirs worldwide, and there's so much sediment stored in them. It seems like you could maybe pull this out by looking at the published studies of those, the numbers of those, where they're located, how much sediment they might have trapped.
Yes, definitely. Yeah, there are a lot of good studies, and the sediment model that I mentioned that WM said also includes that sediment trapping from dams. And there are a lot of efforts underway, including, for example, the Elwha, where they release that sediment by breaking up the dams, or you can release it in other ways as well. But in a part, the dams are not the only problem, or the trapping of sediment behind the dams is not the only problem. You also change the hydrodynamics, of course, of the hydrology of the river itself. And that also changes the ability of the river to move the sediment to the delta. So sediment might also just be trapped under the river downstream of the dam.
Thank you. And Jonathan, as with what I said for Bill, if you want to follow up on that and there's time at the end, please do. Sasha Liebman, from your research, which delta communities around the world do you think are at the highest risk from sea level rise driven morphological change?
That's a good question. I'm not sure if I can get into specific deltas here, but I would say in general, deltas, of course, with the highest rate of subsidence, because that varies a lot more than relative sea level rise rates do, or that eustatic sea level rise does. And also, of course, rivers that have been dammed the most. So those two effects, of course, compound and increase risks on deltas from land loss and also from other flooding issues.
From Lawrence Voulis, great talk, whirlwind of work. I had a question for the comparison of tidal amplitude and wave energy controlling delta sediment retention fraction. Do these findings depend on the relative energy over sediment fluxes from the river?
If I understand that correctly. What I showed you in those plots were simply wave height versus retention. So that there is no sediment flux in that necessarily. Although, of course, sediment flux itself also has a big impact on sediment retention. But because that's in the formula, it's a little hard to pull out independently, because that's why I didn't show it. But yeah, sediment flux and discharge itself also have a big impact on sediment retention.
All right, from Roman DiBiase, again, great talk. I am curious about the ternary diagram showing your global compilation. Do you think the contrast in number of channels is more driven by sediment flux or wave climate?
That's a good question. So, of course, like R is a first, like that ratio R I mentioned is a first order control on the number of channels. And that R dictates morphology. And then for wave dominance, we almost exclusively see single threaded deltas. And then if you exceed R, you get into a regime where you bifurcate and get multiple channels. And all of that likely also depends on the size of the delta, which again then scales with the fluvial sediment flux. So in that sense, I would say that fluvial sediment flux is a little more important than wave energy, because that also affects delta size, and that's and just time scales to build mouthbars and to bifurcate.
That makes me wonder about the geologic record of deltas. Makes me wonder what can be backed out. It's not a question for you, but you probably have thought about this.
Yes. Right. Yeah, no, that's something that's kind of, oh, sorry, go ahead.
Go ahead. You go ahead, John.
Okay, that's been on the back of my mind a lot. I really haven't had time to go into that. But of course, like these connections between morphology and boundary conditions is something that would be really cool to try looking at ancient deltas and what you can detect of those morphologic indicators and what can then say about the paleo environment. Definitely.
And there are some neat people one could work with on that, you know, who are looking at that sedimentary record. All right, so Jim Best, again, great talk and congrats on the award. Have you tested these ideas on delta growth / form for freshwater lacustrine deltas? I'm just wondering if this would help narrow down the effects of density changes at the delta mouth on the effects of waves versus Q on sediment dispersal.
That is also a good question, a very short answer. No, I have not tested this for different salinity regimes, and that would also be a great idea. No, no, but yes, it would be a cool thing to try.
Okay, the next one, Noah Snyder. Can you comment on the role of sediment trapping behind dams on delta change from your global data set? We might have touched upon this a little bit already, but...
Yeah, a little bit. One thing that I didn't discuss very much, because I showed all those arrows within that ternary diagram highlighting how deltas might change. So we did look into WMZ simulations comparing pristine fluvial sediment fluxes, so before dams, and then disturbed sediment fluxes, so after dams and other land use changes. So from that, we found that the changes in sediment flux, and so before dam, after dam, have an observable impact in the amount of delta growth rate. So delta growth rate that we observe in Landsat are primarily controlled, of course, by the amount of fluvial sediment flux feeding the system, but they're also controlled by the relative change that an individual delta has undergone. So with a bigger reduction in sediment fluxes, primarily because of river dams, we find a larger, we find less delta land gain or delta land loss.
What I like about your work in particular is that you can do what you just did. You can evaluate different conditions, you can boundary conditions, you can predict, you can make predictions that are testable. And it's just fascinating that land, coast, marine interaction of all the things happening at that boundary are just amazing. All right, that's the last question I have. Go ahead.
Oh, no, I was to take it's been fascinating that we now have about 30 years or so of Landsat, and the coastal area is changing fast enough that we can test a lot of our theories based on that record. So that's been a really exciting avenue.
Can you say a few words about what you're doing next then?
Yes. So we're looking into that aspect of sediment retention. Is one thing. So how much of the sediment fed to the system is actually maintained within the delta? And over long time scales, of course, not only sediment is retained, but also other things like nutrients and carbon. And if you then, with the theories that we've developed, extend that over long time scales, we find that the deltas might have they have the potential to really be significant players in things like the carbon budget or other important biogeochemical cycles. So that's one of the avenues we're kind of tinkering towards.
All right, let me check to see if there are more questions. There is a follow-up from Bill Dietrich. Shouldn't grain size matter for delta morphology? And what about delta subsidence influence?
So yes, grain size is definitely important. And for example, it feeds into a lot of the case that I mentioned, so that alongshore sediment transport is probably affected by grain size, and hydraulic geometry of a channel is affected by grain size. So yes, the downside is that we don't, or I'm not aware of any data sets of for example, sediment distribution along rivers. So that would be great, and we could do a lot with that data, but I don't think it's there yet. We're right about now getting into predicting bed load fluxes versus the existing suspended load fluxes that we get from WMSET. But there's still a lot of ground to cover there. And the second notion on delta subsidence, it's implicitly in the sea level rise that I mentioned. So I simply add the kind of marine portion and the delta portion by adding the regional sea level rise, primarily from climate change, and then the local delta subsidence from a subsidence model that is fed by a global groundwater model from PCR Glove, from a model here at Utrecht. It's a really rough model, and subsidence has been really difficult to get right at this scale, or at any scale, I think, but especially the global scale.
Are any of the large reservoirs on Earth behind some of the biggest dams, can they be used? Can you evaluate your model? There's no sea level rise, but there's a delta forming, and there's a flux, a sediment coming in. Is there something? Can you?
Yeah.
Can
yes.
You look at delta growth?
That's yes. You're reading my mind. So no, we're thinking about that. So one of the ways that we're trying to, that's not something we've done yet, but it's in a proposal. So like all of those deltas that are formed as kind of bayhead deltas in those reservoirs, that they're kind of deltas that are faced with an extreme jump in sea level over a very short time scale when they filled up the reservoir. So no, that's a really good analog for a lot of the other deltas that we find, especially concerning how deltas prograde. For example, when sea level rise slowed down 6,000 years ago for marine deltas.
Mm-hmm. Well, thank you. I think we're near the end here. Thank you so much. It was fascinating. It was a fun way to spend the last hour. And I think a good way to kick off a party. So I do want to remind everybody that it's traditional for us to head off to a reception. And although we're all going to be doing it from our rooms somewhere on Earth, we can do it in this Wonder platform that I've posted into the chat box here. So if you go up to the chat, you'll see near the beginning that I posted a Wonder link, and there's a password. If you go to that, you can go there and congratulate Jap in person. Once you get there, several of the members of our social media group are going to be there to explain to all of us how this will run. I did a test run with them yesterday, and it was really fun. I have to say it's way more fun than a Zoom meeting. So please join us and take a chance to meet with Jap in that room when you get there, the Wonder platform. And I'd also like to say that we are thankful to those who nominated him and who wrote letters of support. and all the people who've been in the review group that reviewed all those other nominations and yours as well. Just overall a large body of exceptionally wonderful work from you and others. Thank you. All right, everybody, have a good evening. I hope that we'll see you over at the Wonder Party.
Right.
Right.
Bye-bye.
Bye-bye.